All right, so we're back to chapter 8, second video of the chapter. We're going to talk today, right now, here, about potential energy. And I want you to keep in mind as we go what we concluded with the last video, which is that every single force in the world can be considered conservative or non-conservative. Okay? Two kinds. Conservative and non-conservative. The conservative ones do zero work when an object moves through a closed path. The example was the block. The mass, the 1 kilogram mass that we lifted up for a meter, then brought back to rest. It turns out that the work done by gravity for that round trip was zero, that closed path. Okay. Would have been zero no matter what we did with that. As long as we brought that mass back to the original position, the total work done by gravity, a conservative force, is zero, as long as it's a closed path. That's what makes a conservative force conservative. If that does not happen with a certain force, like the case of friction, it's not a conservative force. Okay? So, keep that in mind as we move forward. Potential energy. In contrast to kinetic energy, which we've already seen, K. I'll get to this little picture in just a minute. K is always equal to 1/2 mv squared. And that does not matter what force got the object moving, whether it's a baseball or a car or the Titanic or an electron, whatever the mass m is, doesn't matter. Its kinetic energy is always 1/2 mv squared, regardless of what force got it going. No matter what force gave it its speed. Okay? That's always true. But potential energy, which goes by, believe it or not, the symbol U. Okay. U, how do I have it written here? I've got it written here. Equals, well, there's not a single expression. There's a different expression. Again, how do I have it worded? Okay. For different conservative forces. So not every potential energy U, or potential energy U, has the same expression. All kinetic energy is the same, but potential energy will depend on the force that we're talking about. K doesn't depend on the force, but U does, as we shall see. Okay? So what we have here is a bowling ball. All right? So again, sort of pigeonhole this. We're going to come over here now to our bowling ball, and we're going to lift our bowling ball. It's a 10-pound bowling ball, which is about 4.5 kilograms. We're going to lift it up and put it on a rather high shelf, 2-meter high shelf for storage. Okay? But that takes work, right? That takes work to lift that thing up. Okay? But the nice thing about gravity is when you put that bowling ball up there, the work that you did is not lost. It is stored in what we call potential energy. The bowling ball here has more potential energy than it had on the floor. We have taken that work and put it into a thing that we call potential energy. Potential energy is kind of like stored energy. It's stored up and ready to be released into different forms of energy. Okay? That energy has not been lost. There is a connection between the work done by gravity as we move the ball from there to there and its change in potential energy. I'm simply going to write it down. We're going to unpack it a little bit. The work done by conservative force, W sub C, means the work done by any conservative force. And so far, we've only said that gravity is conservative. Okay? Is equal to negative the change in potential energy. Okay, now that will seem highly cryptic to you, even if you are staying totally on top of all physics, okay, in your life. This will seem cryptic to you. Okay. Hopefully it will not remain so after the next video or two. This is like our starting point. The work done by a conservative force, in this case gravity, is equal to the change in the potential energy of the object. In the case I've got here, the work done by gravity, okay, as we move it from the floor to the ceiling, from the floor to the shelf, is equal to the change in this object's potential energy. All right. Now let's be a little more specific. I think I've said what I need to say. Oh yeah, potential energy is in joules, right? It's plain old energy. Okay. So this is a change in potential energy. Okay. It's a change in potential energy. Now, it turns out that for gravity, if you look at the work done by, I'm not going to go through the derivation. It would probably take about 5 to 10 minutes to do it right. But if you look at the work done by gravity, which is a conservative force, we will see that the potential energy for gravity is mgy. This is for gravity, where y is the height, right? Is the plain old, same old y we've always dealt with. Okay. Now, gravity is a conservative force, as we've already said. There is one other conservative force that we have talked about. And I'm just going to mention it briefly here. We're going to come back and do an example using it in a couple more videos. But another conservative force is the spring force. And it turns out that its potential energy is equal to 1/2 kx squared. Okay. So, as advertised here, U is different, has a different expression for different conservative forces. Here we have two different conservative forces, the only two that we're going to see this semester. These are the only conservative forces we're going to see this semester. We'll see at least one other next semester. Okay, so these are our only conservative forces. So each conservative force has a different potential energy. Every conservative force has a potential energy associated with it, and that's the connection between them. And yes, I'm going to return to our bowling ball here. Okay. Let's look at this expression for the gravitational potential energy. Okay. Make sure I got everything I need here. Have I said anything? Yes. Okay, let's find out what happened when we moved this block from this block. This is not a block, this is a bowling ball. This 10-pound bowling ball from the floor to the ceiling. In fact, let's figure out what its potential energy is in both cases. Okay, let's see, U initial. It's initial, this is the initial position. This is the final position. Its initial position is going to be mgyi, right? Its mass is not going to change, but its position on the vertical axis will change. This is equal to 4.5 kilograms times our old friend 9.81 meters per second squared times, what's yi? Well, depends on what we call y equals 0, doesn't it? Look, this is important. The temptation, or the temptation is the wrong word, the obvious choice is to call yi 0 and put the origin on the floor. If that's the case, then y final will be what? Yes, 2.0 meters. So what's the initial potential energy of the bowling ball? It is 0. It has no potential energy whatsoever. And what's its final potential energy? Well, it's going to be 4.5 kilograms times 9.81 meters per second squared times YF, right? Which is 2.0 meters. So its initial, right, starting from the ground, going to the shelf, its initial potential energy is 0 joules. Its final potential energy is it 88? I think it's the number I got. Yes, 88 joules. Okay. So that the change in potential energy is UF minus UI, which is 88 joules, minus 0, which is 88 joules. So its potential energy increased by 88 joules when we lifted it. Can you read that? My pen's getting a little weak. Its potential energy increased. The change in potential energy was 88 joules. Its initial potential energy was 0. Its final was 88 joules. So its change was 88 joules. Okay. Now I'm just going to draw in this section here. I'm going to do one more thing. Well, the last thing I want to tell you in this video, and it's hugely important, so don't get fuzzy, okay? Stay frosty here. Stay tuned in. It is this. It doesn't matter what you call 0. Suppose we had done the same thing. Suppose we had taken, we did a different thing here. Suppose we had called the shelf 0. If that was the case, what would yi equal? We're calling up positive. Yi would be minus 2.0 meters. In other words, it doesn't matter where we put the origin. Okay? So all of this is with yi equals 0. That is, it's starting on the floor. The floor is what we're defining as the 0 of our vertical number line. But what if we said that yi was minus 2 meters? What if we did the same calculations now? What we would find is this. We would find that ui is equal to minus 88 joules. If you go through mgyi, the mass 4.5, g 9.81, y sub I negative 2. All we've done is put our 0 up here now instead of down here. Okay? You multiply those together, you get negative 88 joules. What is your final potential energy? Well, finally, the ball is up here at 0. So the final potential energy is going to be 0. So the individual values, look, the individual values, pick a better color here, of the potential energy change. What was 0 joules now becomes negative 88 joules. UI, initial potential energy, was 0, now it's negative 88. The final potential energy was 88, now it's 0. But One thing has not changed. Delta U, the change in potential energy, UF minus UI, is going to be 0 minus 88 joules. So delta U is going to be 88 joules in both cases. It doesn't matter where you put your origin in the y direction. It doesn't matter what you call y equals 0, because it is the change in potential energy which is the physically important thing. These individual values, UF and UI, which change, it was 0, now it's negative 88. It was 88, now it's 0. Those individual values are not significant. What is significant is the change in the potential energy, because it is that is related to the work done by the conservative force. That is the important thing, and that doesn't change. Doesn't matter where you put the 0. In other words, final point, what you call y equals 0 is arbitrary. But once you pick it, you have to stay with it. You can't move it around in a given problem. You have to stay with it. Whether you put it on the floor or on the shelf or anywhere else, in the basement, in the attic, somewhere between the floor and the shelf, doesn't matter where you pick it, as long as you stick with it.